numerical integration. Or you can also say approximating integrals. Approximating integrals. Now the question is why we need to do this. So there is always a why question. Why we wanna do numerical integration. That means can't we integrate all the functions that we have? So for example, let's look at these. So there are certain functions that what we call the non-elementary integrals. So non-elementary integrals. So what are non-elementary integrals? So for example, if you look at these integrals, sine x squared dx, or similarly cosine x squared dx, or e to the x squared dx, or the very famous e to the x squared, e to the negative x squared dx, the Gaussian integral. And then we have more. We have 1 plus x to the fourth square root dx, and 1 over ln x dx. 1 over ln x, but if you have just ln x dx, we can do that using integration by parts. And also we have sin x over x dx, and also we have I can give you just maybe one more. For example, 1 minus k squared sine squared x dx. So this is what we normally call the elliptic integral. Elliptic integrals. So there are certain integrals that for example, the first integral appears in optics in physics, and then the third integral appear in probability theory when you do a Gaussian or the normal distribution functions. So and then again the elliptic integrals appears in a lot of mathematical physics situations. So these are certain integrals, but unfortunately we cannot get the answer using elementary functions. Elementary functions means basic radicals, sine, cosine, exponential functions, things like that. So you cannot get these answers to any of these integrals using them. Okay, so there are we should say cannot write answers using elementary functions. So elementary functions mean pretty much all the functions that you know, all kind of functions that you know. Like if you go to advanced calculus classes or graduate level, there are certain like new functions, what we call hypergeometry functions, stuff like that. But those are not elementary. So those are what we call generalized functions. But what we are saying is you cannot integrate any of these functions using the function that you know. Functions like all the radicals, polynomials, sine, cosine, inverse sine, inverse cosine, exponential functions, like that. Okay, so that means now the question is, that means there is a need to do this somehow, because we cannot just say that okay, we can integrate, I'm done. That's not a valid argument. So what we need to do, we need to find to do it somehow, because for example, like let's say you have a project and you get an integral, and let's say you end up with one of those integrals. So can you say like I cannot integrate this one, so I'm done with the project? So you cannot say that. So that means we need to, even though we cannot do exactly, what we can do is we can do some approximations. Okay, so what we're trying to do now is we're gonna approximate the integral. So it's not the exact one, but approximation. So so we have what we call approximations. So so we all know like certain approximations. For example, one that you learn in Calc 1 is a Riemann sum, remember? So Riemann sum. So Riemann sum is one of the first one that we study. So what we did was, do you remember what we did? So let's say we have a graph. So this is a graph. So what we try to do, we try to find the area below the curve. So that's kind of the idea, because we know that the integral is represented as the area below the curve. So what we normally do is we're going to split this into equally spaced. Why we make it equally spaced? Just to make the calculation easier, but that's not the best way to do it, but it's going to make the calculation much faster. So we're going to cut this into equal parts. So let's say we're going to cut this into 4 parts for the moment. So then so this is the first one, second one, third one. Now what we do, so and then we can say the gap. So if you go with A to B, so if you cut into 4 parts, so this is one such gap, what we normally call delta x. So delta x is normally written by B minus A divided by the number of parts. So if you cut into 4 parts, it is B minus A over 4. So like that. And then what we do, so that's the gap of 1. So what we're trying to do is we can approximate this using rectangles. But the question is, when you want to find the rectangles, there are no rectangles here. So what we do, we want to make rectangles. So how we do it? We can pick some representative values. For example, so you can pick, so there are options. So so the representative value for such interval, so you have a lot of options. So you can pick the left endpoint, or you can pick the right endpoint, or you can pick the middle point or midpoint, or basically you can pick any point. And then you can see that if you cut this into a lot of parts, all those 4 answers going to be very close, not exactly the same, but very close to each other. But if you cut into a few parts, you can see a big difference depending on how radically change the function. So let's do one such situation. Let's say we're going to pick the left end point. So you can say the so we can have a notation for that. We can say the Riemann sum using left end point, Riemann sum using right end point, Riemann sum using the midpoint. So those are the 4 common ones. So let's go with the left end point. So if you go to the left end point, so the first interval, I'm going to pick the left, this is as the representative value. So that means your approximation is this. So this you're going to consider as the approximate value under the curve, and you can see that there's an error. So that means this is the error in this one. So because we're going to ignore that part and do the same thing. So we're going to go with there. So you're going to go like that. So there's like a slight one part out, one part in. So there's an underestimate and overestimate. So still it's not exactly equal, but we like a little better than the previous one. Also now for the next interval, I'm going to pick this one as a representative value. So that is the value. So it's definitely an overestimate. So so that's the approximate value. And here you're going to pick that one. So that's the value. Now what we're going to do, we're going to add all those 4 areas. Once you add those 4 areas, you're going to get approximation to the integral, okay, sum of the areas. So that means we can write the integral of this function, if you call it y equal fx. So what we need to do is you need to evaluate the function at those points. So I'm going to call it x0, and then x1, and then x2, and then x3, x4. So in this case I need to evaluate only at x0, x1, x2, x3, because we are looking for the left end point. If you pick the right end point, you need x1, x2, x3, x4, and also you can pick the middle point, you know. So you just calculate the middle point and find the value. So middle point would be the best in this situation, because there's underestimate, overestimate cancellation most of the time, except in the last one in this case. And then you get like kind of much better values for that. So but in this case, what's going to happen is your integral a to b fx dx, that's the area under the curve, is approximately equal to the sum of areas. So sum of areas. So this is what we learned before in Calc 1. So we can see that we can pick any of those points, and then you end up getting different values depending on the kind of curve you get. So if it is increasing a curve, if you pick the left hand point, that's going to be underestimate because you always get the lowest. And if it is increasing function, if you pick the right hand point, you always get a overestimate because you finding the larger value. So it's, so depending on the curve, it can be underestimate or overestimate. But the thing is that what we're trying to do right now is we can do better. We're gonna go for another new method. We're gonna discuss two new methods in this section. So let's talk about them. And the first one is what we call the trapezoidal rule. So this is a new technique called the trapezoidal rule. Trapezoidal method or rule. So what we do in this method is, so let's look at a situation. So this is your curve. So what we try and do as before, so this is your interval which is going from A to B. As last time, what we can do, we're going to cut this into equal parts. Why we do equal? Just to make the calculation easier. So we're going to go with from here to there. So you can start with x0, that's your first value, and then your last value we normally call xn. So you can cut it into n parts. So you're going to go with x1, and then we're going to go with x2, like that. So this is the ith part, so it is we can say the kth part, so xk, and then go like that, and this is the xn minus 1. So we can assume that they are equally spaced. So if they are equally spaced, so one such part is what we normally call delta x. So the delta x is given by b minus a divided by the number of parts. So this is always the case. It is b minus a divided by n. That's the interval, and then that's the gap of one such division, and the n is the number of subintervals. And then what we're gonna do, after we do that, then you can find the ith one. So what ith one is x0. You're gonna add I many such gaps. So that is the ith one. So that if you add one gap to the x0, you're going to get the x1. So like that. So that is the ith x coordinate. Okay. So the ith x coordinate. Ith x coordinate. Now what we can do, we can evaluate the function at this ith. So we're going to call it yi. This is fxi. So you can evaluate the function at the ith one. So those are the function values. So you get the function values. So function value. So you can evaluate the function at those values. Okay. So now what we're gonna do, we're gonna look at the trapezoid. So so I'm going to draw the trapezoid here. So that's the trapezoid there, and the trapezoid at x2, and the trapezoid at xk. So I'm going to actually draw that, and then the so like that, and then we have other values. Okay, so like that. So what we're going to do, we're going to draw the trapezoid now. It's not just the left hand point, right hand point. We're going to draw the actual trapezoid. So that means we're going to do that. You're going to combine that, and then combine this, combine that. So we'll combine them using trapezoids. So that's how we call the trapezoidal rule. And then what we can do, we can evaluate the function at those points. So in this case, it is a yk, and then y k plus 1, like that. So this is y0, y1, like that. Okay, and this is yn. So what we can do now is we're gonna actually find this area of the trapezoid. So so if you kind of little bit exaggerate this, so this is what's gonna happen. So this is one such trapezoid, so and that's the curve, and this is the trapezoid. So so we can approximate the area under the curve by the area of the trapezoid. So this is what we're gonna do. So we're gonna use this area as the area below the curve. That's one we're gonna use as the area below the curve. So that's approximate value, and you can see that that's approximation. Good. So we have, so this is the kth one. So we have xk, and then this is xk plus 1. So this is yk, this is y k plus 1 and then this is the gap. This gap is delta x because we divide them equally. You don't have to do that, but you can. So in this case, what's going to happen is, so in general, the area of a trapezoid, what's the area of a trapezoid? Area of a trapezoid is, so if you have a, I'm going to draw it here. So if you have a trapezoid, so it looks like that. We have two parallel sides. Those parallel sides we normally call A and B, and then there's a height. So the height we normally call h. So the area is given by what we normally write is half h. You add the two sides. So this is very easy to prove using simple geometry. So this is the area of a trapezoid. Area of a trapezoid. Area of a trapezoid. Area of a trapezoid. So we can use the same idea here. So what we can do, we're going to find the area of this trapezoid. So this is the kth one. So we can say this is area of delta, means area. So area of the kth one, that's the notation we use. So that's a small area of this trapezoid. We're going to call delta a k, the kth one. So it is simply given by half. The gap is, the height is delta x in this case, and the two sides are yk plus yk plus 1. So that's going to give you the area of one such trapezoid. Okay, area of one such trapezoid. Now what we can do, we're gonna add more and more. So what we want to do is we're gonna calculate this at each such sub interval. So that means we can start with the first one, x0 to x1. So we can do a calculation for the first sub interval, and then we're going to calculate that for the second sub interval. So keep doing it, and that's xk1, and then we just keep doing it, and then we end up getting xn1. So we're going to do one such calculation for each. So that means you can write the formula now. So your formula going to be, so the area a to b fx dx is approximately equal to the sum of such sum of the areas of such trapezoid. So it is starting with 1/2 delta x, that's common, and then start with the first one. In the first one we have y0 plus y1. Those are the two sides, and then from the second one you're going to get y1 plus y2. Just keep doing it. In the last one you're going to get yn minus 1 plus yn. So, and then you can see that there's a nice simplification going on. You can add these two. You see that, the y1, and then you can add this one in the next one, you can add this one in the next one. So keep adding. So that means if you do that, then you're gonna end up getting, you can see this is equal to 1/2 delta x. You have y0 plus, you can see these are all twice, so 2 times y1, 2 times y2, keep doing it, and 2 times yn minus 1 plus yn. So only the first one and the last one have 1 1, everything else has 2 2. So the pattern goes like this. So it is a 1 2 2 2 and then 1. So that's the pattern, that's how we remember the pattern. So it's a 1 and then 2 2 2, and then at the end you're gonna get a 1. So this is what we call the trapezoidal rule. Trapezoidal rule. So you can see that this is like kind of very simple rule. What we need to do is we need to evaluate the function at those node points starting with y0 and then all the node points, but in the middle you need to multiply by 2. So it's simply a calculation of the function. So you can use a calculator for that. So that's it. Okay, so let's do an example from this just to see how things going on. Okay, so again, so what's the rule? So it is a to b fx dx is approximately equal to 1/2 delta x, and then we have y0 plus 2y1 plus 2y2 like that, and then 2yn minus 1 plus y0. So this is the trapezoidal rule, where delta x is b minus a over n, not over 2, over n. Over n. N is the number of subdivisions, so it's a comma. So this is what we call the trapezoidal rule. Trapezoidal rule. Trapezoidal rule. So let's do an example just to see how things are going on. So the example, use the trapezoidal rule. Use the trapezoidal rule with n equal 4. What is n? Means number of subintervals. Number of subintervals. To estimate 1 to 2 x squared dx. Okay, so if you get a question like that, so it's very common. If you get a question like that, the best thing would be just to draw the number line and mark those points. So we have 1, and then so what is delta x? So it is b minus a over 4, or n. That means b means 2, a is 1 over 4. So you're gonna get 1/4. So in other words, 0.25. So that's a gap of one sub interval. So that means it's going to start with 1, and then it's going to go to 1.25, and then 1.5, 1.75, and a 2. Okay, so so each gap is 0.25. Okay, so that's the those are the numbers. So it's always a good idea to mark them, because it's going to make the calculation much easier. And then now we can just use the formula. So what the formula says, it says 1 to 2 x squared dx approximately equal 1/2 delta x and y0 plus 2y1 plus 2y2. So what we have here, we have a x0, x1, x2, x3, x4. That means the corresponding value is y0, y1, 2y2, 2y3 plus y4 according to the formula. So 1, 2, 2, 2, 1. Okay. Now what we can do, we're going to plug in the values. So this is equal to, the first one is approximation, the second one is equal sign, 1/2 delta x is 0.25, that's the gap, and then evaluate. The function is y equal x squared as a function, so we're going to plug in there. So that means 1 squared, then 2 times, so let's fix that. So it is 2 times 1.25 squared, and 2 times 1.5 squared, and 2 times 1.75 squared plus 2 squared. That's what you get. Now what we're going to use a calculator, and please, when you do homework problems, make sure that you're gonna write the answer according to the number of decimals they ask for. Okay, so that's one thing where we can you might see you answered wrong because you did not give enough number of decimal places. So if you use a calculator and if you write for 5 decimal places, you have to round it. Okay, so it is 2.34375. So that's what you get as the approximate value. Okay, so let's do the actual calculation and see how close this is. So if you do the actual integral, it's 1 to 2 x squared dx, because this one you can do actually, so you can test. So this is a test. Okay, we're gonna check. So it is x3 over 3 to 1. So this is 8/3 minus 1/3, so which is 7/3. And then what we can do the percentage error. So let's do the percentage error. How do the percentage error? Percentage error means the approximation minus the exact value. Take the absolute value because we don't need the whether large or not. So and then go with the exact value. Again, use the absolute value just to make sure that you get positive answer, and then take the percentage. So this is what you call the percentage error. Actually, if you do that, so if you plug in the values, you're gonna get 2.34375 minus 7/3 absolute value divided by 7/3 times 100. You're gonna get something like 0.446%. So that means you can see that the error is less than 1%. It's less than 1%. So it's roughly 1 out of 200 is the error. So that's not too bad, because you can see that just doing like 4 sub intervals, you can get the answer which is correct up to this many decimal places. So it's like it's only a 0.5 error per 100. So this is like a really good situation. So this is what we call the trapezoidal rule, but you can see that the results are excellent. Okay, so you're gonna get the excellent the correct values just by using the trapezoids. And then and soon we can talk about another method that's much better. That's called the Simpson rule. But here this is just you just draw trapezoids and calculate, and you can see that the answer is like much better. So so let's do one more example just to see how things going on. So the next example, so let's say use trapezoidal rule. Use trapezoidal rule. With let's say n equal 5. With n equal 5 to estimate the integral from 0 to 1 e x squared dx. Good. So let's do the same kind of calculation here. We start drawing the number line. So then numbers go with 0 to 1. Your delta x is b minus a over n. So it is 1 minus 0 over 5, which is 0.20. So it is 0.2, and then 0.4, and then 0.6, and then 0.8. Okay, so those are the x values. So if you want to call it, we can call it x0, x1, x2, x3, x4, and x5, and the corresponding y values are y0, y1, y2, y3, y4, and y5. So then we can do the calculation. So it is 0 to 1 e x squared dx, which is approximately equal. Never write equal, this is never going to be equal. So the 1/2 delta x. So let's write the expression. It's always a good idea to write the expression first. So it's a y0, 2y1, 2y2, 2y3, and then 2y4, and then y5. Does that happen? For example, this is that one, so we can evaluate the value at this point and plug in there. So like a situation like that. So let's plug in the values now. So so we're gonna get this is equal 1/2 delta x. You already calculate, that's 0.2, and then we can do the y values. So it is e to the 0 squared plus 2 times e to the 0.2 squared, and then 2 times e to the 0.4 squared, and then 2 times e to the 0.6 squared, and then 2 times e to the 0.8 squared, and then e to the 2. So that's what you get. So now what you can do, you can use a calculator. Remember, you have to square first because the power comes first. So you square first and then plug in that value to the e, and then you multiply by 2. So if you do that, you end up getting 1.48065. I think try to do this calculator and see whether you can get this answer first before you try the homework, because you should get this answer. So always check how many decimal places you need, and then give correct up to that many decimal places, and then yeah, so this is what you get. So if you do this calculation, okay, good. Now so you can see that it's not that difficult. You just need to plug in the values. Let's talk about the next method, or what we call the Simpson rule. So this is very good method. The next one, this is what we call Simpson rule. Simpson's rule. Simpson rule. So what is the Simpson rule is about? So let's say, so this is your graph. So let's say you have this graph, and then as before, you again gonna divide this into equal subintervals. So we're gonna start with a, that's a, and then this is the n, n parts of b. Okay, so we still gonna divide into equal subintervals. But what is different here? So what we gonna do, not as before, this time we gonna divide into even number of subintervals. So we can divide this into even number of subintervals. So n is even. N is even. That's the first condition. N is even. And then again the same formula. So delta x is b minus a over n. but the thing is that n is even, so you can divide into even number of subintervals. That's the first difference compared to other methods. So now let's see how it works. As before, we can evaluate, we can have x1 and then we have x2 like that. So this is xn minus 1 like this. So let's say you know these values. These are the function values. So you have this value and the value and the value. So what we're gonna do, not as before, we know that there are 3 points here. There are 3 points. So if there are 3 points, you can show that there is only one parabola going through those 3 points. So what we're gonna do, so we're gonna pick those 3 points. So let's look at the situation. So we have 3 points. So we're gonna pick 3 points. So we have these 3. Those are the heights. So this is the function. So what we know is so let's say this is your actual graph. You know, it can be kind of difficult, so it can be anything. So that's your graph, actual function that you try to approximate. Let's say it goes like that, but what do you know? So that's your actual function. So this is the y equal fx. But what we know that there is a unique parabola passing through these 3 points. So that's that parabola. It's a unique parabola passing through these 3 points. Why is that? Because we know that when you write a parabola, it is like a x squared plus b x plus c. There are only 3 unknown. You can see that there are 3 unknown. So that means there's a unique parabola, because those 3 you can find using these conditions, because you know that if it goes through these 3 points, then you can write 3 equations, you can solve. Okay, so that means there's a unique parabola. Okay, there's a unique parabola passing through these 3 points. So now what we're trying to do, we can approximate the area under the curve by the area under the parabola. That's what we're trying to do. So we can approximate the area under the curve by the area of the parabola. So what we can do, we're going to use this area instead. We can use this area instead. That's the idea here. We can use this area, and you can see that when you try to find the error, you can see that this one has a much less error compared to the trapezoidal rule. Okay, so and then so what are these points now? So we have y0, and this is the y1 value, this is the y2 value. So what we do, we can assume that there's a unique parabola which has ax squared plus bx plus c form, and then you can show that if you do that, this area of this region is, I'm going to skip that part. You can show that if you consider the gap is h, there's a h and there's h, and you can show that it is h divided by 3 y0 plus 4 y1 plus y2. You can show that. Okay, we can show this. So I'm going to skip this argument but we can show that if you try to find this area, you're gonna get this formula. Okay, so we can show this. We can show this. We can show that this area of this region is given by this formula. This is h divided by 3 y0 plus 4y1 plus y2. So you get 4 times the middle one. So that's why you always need to have 2 together to do this. Now what we're gonna do, since we know the area of those two, see, you can see that it's only depend on the gap and the function values. So h is the delta x in this case, and then you can just consider 2 at a time, and then you can write the formula. Okay, so so that means, for example, in this situation, so if you consider the first 3, so if you consider the first 3, so what we can do, we're going to consider the first 3 and then the next 3, like that. So so that means you're going to end up getting this formula. So from the first 3, you're going to get h over 3, h is the gap or delta x, it is y0 plus 4y1 plus y2, and then if you consider the second 3, you still get h over 3. The starting one is, if you go to the next 3, you can start at y2 because you have y0, y1, y2, so it's gone. Next, if you go to the next 2, if you go to the next 2, you're going to get starting with y2, so it's a y2, and then 4y3, and then y4. Keep doing it. You always consider 2 at a time, and then you write it. So for this one, I'm gonna give you that. That's starting with y2. So just keep doing it, and that is what we call the trapezoidal rule. So when you add them, you're gonna get the formula. So let's write the formula for that. So not trapezoidal rule, it's a Simpson rule. So the formula is, so let's write the formula. So the Simpson rule. Simpson rule. So we need x0, x1, x2, and then xn is an even number, because you always need to group 2 at a time. Okay, so that's what we have. So the Simpson rule is it is a to b fx dx is approximately equal to delta x over 3. We have, what is the delta x? Delta x is, as before, b minus a over n, but n is even. Okay, it has to be even. That's the only difference here. So you're gonna get, so let's start the formula. So it is y0 plus, but you can see that if you look at the previous slide, you can see here this y2 and y2 get doubled because you stop with y2 and you start with y2 again. So that means you, when you add them, that get twice. Okay, that get twice. The other one has a 4, that get twice. That means, so that will be reflected in the formula. So what's gonna happen? It is 4y1 and then 2y2 and then 4y3 and then 2y4, like that. So see the pattern, and then it's gonna stop with 4y n minus 1 plus yn. So that is the formula. So that means the pattern here is 1 4 2 4 2, like that, and it's finished with 4 and 1. So that's the pattern: 1 4 2 4 2 4 1. Okay, so yeah, so this is the Simpson rule. That's the Simpson rule. And you can see that it's not that difficult, but you have to remember the pattern. So it is a delta x over 3 now, and then you always need to divide into even number of parts because you consider 2 at a time. You consider 2 at a time. Okay, so let's see this in example. So use the Simpson rule. Use the Simpson rule with n equal 4 as even number to approximate 0 to 2 5 x to the 4th dx. So again we draw the line, so it's easy to do it. So 0 and then delta x is what? Delta x is 2 minus 0 over 4, so that means 1/2 or 0.5. So if you go with 0.5, so it's a 0.5 and then 1 and then 1.5 and a 2.0. So those are the points. So this is y0, y1, y2, y3, y4. So you can see in the formula all the odd coordinate points has a 4. Odd coordinate points has a 4. Okay, so that means I got the formula. So you're gonna get yeah, I need to write that again. So you're gonna get 2.0 and this is divided by 4. Okay, so so the 0 to 2 5 x to the 4th power dx is approximately equal delta x over 3. So let's try the formula. So it is y0 4 y1 and then 2y2 4y3 and then y4. So that's what you get. So let's plug in. Delta x is 0.5, so it's a 0.5 over 3, so it's a 5, and then we have 0 to the 4th power plus 4 times 5, 0.5 to the 4th power plus 2 times 5, 1 to the 4th power and then 4 times 5, 1.5 to the 4th power plus 5 2 to the 4th power, and then you can use a calculator. And actually this one you can do fractions if you want. So if you do need the exact value, is 32 1/2, so that's what you get. And also you can do the you can use a calculator to get this answer. Okay. So that's the situation, but you can see that you just need to plug into the formula, but remember the formula has a special pattern. Here we need to divide delta x by 3, and then the y values go y0 for y1 2, so it's a 1 4 2 4 2 1 and with 1, and when you get a 2 when you add two such intervals together. Okay, so you always go with 2 at a time. So 2 at a time, but once you get the formula, you can directly use the formula. But when you derive, you remember you combine 2 at a time. Okay, you combine 2 at a time. Okay, and then the next thing that we need to understand is what kind of error we're gonna get. So let's try to write the error estimate for these ones. So the error estimate. So this is a theorem. So error estimate. Error estimate. So let's go with the trapezoidal rule first. So the trapezoidal rule so what it says, if second derivative is continuous, second derivative is continuous, and it is bounded by, the second derivative is bounded by m, m. I'm going to call it mt for the trapezoidal rule, mt on the interval a b. So we're going to find the upper bound for the second derivative. What is the largest possible value the second derivative can take? That value I'm going to call it m. And once you do that, then it says that the error we call E, error of the trapezoidal rule, is absolute error, is less than or equal, it says that m times m to the t, that's the value that you calculate, and then b minus a to the third power divided by 12n squared. So there's a formula, but we are not going to derive this, but we can use it. What is this mt? Mt is the upper bound of the second derivative, and where n is the number of subinterval. Okay, number of subintervals. So we have a, and then we're going to cut this into n many parts, and then we end with b. So that is the one for the trapezoidal rule. So it has n squared in the bottom. Let's look at what's going to happen with the Simpson rule. So for the Simpson rule, if f to the fourth derivative, okay, you need the fourth derivative is continuous, and the fourth derivative of f is bounded by, now I'm going to call ms. So that's the upper bound of the fourth derivative on AB. So we're going to find the largest possible value of the absolute value of the fourth derivative. Then it says that the error is the absolute error less than or equal ms, that's the upper bound that you calculate, it is b minus a to the fifth power divided by 180 into the fourth power. So that is the error formula. That's the error. This is the error you're gonna get. So it is bounded by this number. It's bounded by this number. So it is ms is the upper bound, and then b minus a to the fifth power 180 into the fourth. The other one is for the trapezoidal rule is mt b minus a to the third power divided by 12n squared. Okay, so there is a pattern, the 3 and a 2 here, 5 and a 4. Okay, and then this is the error. So that's the error, how much error you're gonna get. Okay, that's the error term. So what you need to do is you need to find the derivative. In the trapezoidal you need to find the second derivative. In the Simpson rule you need to find the fourth derivative. Okay, so and then after you know the derivative, and then you can find what is the largest possible value on that interval, and then you can say, so this is the maximum possible error. And you can see that when so this is important, when n gets large, the error gets small. Okay, so when n is large, the error is small. So that's what this says when it's getting larger and larger. But you can see that in the Simpson rule, the error gets smaller much faster because it is n to the 4th power. So you can see error behaves like what we normally call order of n to the 4th. Okay, that means it's gonna go much faster, much faster. In the trapezoidal rule, it's n to the squared. So good. So let's look at an example and see how we can use this in a problem. So so let's do two type of problems. So the first one, so let's do this. Find an upper bound. Find an upper bound. Find upper bound. Upper bound. Find upper bound for the error. Find upper bound for the error in estimating. 0 to 2 5 x to the 4th dx using Simpson rule. With, let's say, n equal 4. N equal 4, not even 5, 4. So the answer, see how it gonna go. So here we have fx equal 5x to the 4th power, and then f prime x is, so we need what for the Simpson rule? We need the 4th derivative. So this 20 x to the 3rd, and then second derivative is 60 x squared, and the third derivative is 120x, and then the fourth derivative is 120. That's the fourth derivative, and it's a constant. So that means your m is so if you look at this in a graph, this is the situation. So let's go like that. There is 120. That is the fourth derivative graph. So the interval is 0 to 2. So the maximum is just that value, because in that interval there's no special maximum. So the maximum value is just that value. So the m is 120. Okay, so the m is ms is 120. ms is 120. Okay, so so this says that the absolute error of the absolute maximum of the fourth derivative is 120. So we're going to pick that value as ms. So that means your error estimate es is less than or equal m b minus a to the 5th power divided by 180 n to the 4th power. So that if you calculate this, 120, 2 minus 0 to the 5th power, it is 180, and n means 4 actually. So n is 4. So it is 4 to the 4, and if you simplify, you end up getting 1 over 12. So that means the so the maximum error, so error max. So maximum possible error is, we said that it's less than or equal to that, so this is 1 over 12 is the maximum error that you can get if you just divide into 4 parts. Okay, just divide into 4 parts. Let's just add one more part to this problem. So let's do like a slightly different problem. So this is the problem. So estimate the minimum number of subintervals. Minimum number of subintervals needed to approximate the integral from 0 to the same integral 5x to the 4th dx, using the Simpson rule. Using the Simpson rule with an error less than, so this is interesting part, error less than, let's say 10 to the negative 4. So let's say you want to approximate this integral with an error less than 10 to the negative 4. So so this is a kind of interesting problem. So that means it is 0.0001. So that's the error. So if there's an error, the error has to be 0.0001. So they're asking what is n? What is n? Okay, what is n? Remember, n is even. Okay, so n is even. So asking what is n? So this calculation is very similar to what we had before, but here they give you the error. So you need to find n. So pretty much we have those same numbers here. So let's see how the rest of the calculation works. So the answer is, we already know the m value, so we get ms. We calculate that before, so m was 120, and we have b equal 2 and then a equals 0 as before. And then we know that for the Simpson rule, your error estimate is, error is always less than or equal to m like ms b minus a to the 5th power divided by 180 into the 4th power. So we know that. So what we need is, we need to make this smaller than 10 to the negative 4, because if you say that is, if this one is less than 10 to the negative 4, then automatically this says that this automatically ES is less than 10 to the 4. So that's what we do. We can use this part of the problem to do that. So that's what we do. We can bound that part. Okay. So now we can complete the calculation. So we can plug in here. So it is 120 2 to the minus 2 minus 0 to the 5th power, and this is 180 in the formula, n to the 4th, which is less than 10 to the negative 4, and we can calculate here. So what we can do, we can cross multiply, and then we can write this one as so we can move n4 to the right side, 10 to the negative 4 to the left side. So then you're going to get 120 and then 2 to the 5 and then 180, and then 10 to the negative 4, n to the 4 goes there. You cross multiply the two, and then this says that if you solve for n is greater than the fourth root of 120, 2 to the 5. You can use a calculator to do this part. 180, 10 to the negative 4, the fourth root. And if you do this calculation, you end up getting 1064 over 3 to the 1/4. You can see whether you're gonna get this answer after you simplify inside. And then if you use a calculator, you're gonna get 21.49. so that means it has to be even number. So this says that n has to, the smallest such n is 22. Okay, so 22 is the smallest such n because it has to be even number, and it has to be bigger than that, so that means it is 22. Good. So there are some applications of this one, like in some engineering problems. So let's do one such, and then that's the end of this. So this is an application. So let's say so there's a lake. Yeah, so let's say there's a lake. We want to find the volume of this lake. So let's say this lake is everywhere 5 feet deep. Some assumptions. Let's say 5 feet deep. So it's 5 feet everywhere. This is a lake, this is a water. Okay, so there is 5 feet deep. 5 feet. And then the question is how to find the volume of this lake. So if you look at from the top, it may look like this. So it may look like that, like this. It may look like this from the top. So what we normally do is we're gonna kind of make measurements. So we're gonna start with the first side. So we're gonna start with this side. You can pick like any side you want. So and then that's the end here. So so what we normally do is we're gonna divide this into equal parts, so depending on how large it is, and then we're gonna use the Simpson rule to find the area. Once you get the area, then you can multiply by the height to get the volume. Okay, so so let's try the problem here. A town wants to drain. Okay, a town wants to drain and fill a small swamp. Okay, small swamp. It is 5 feet deep. That's a good information. About, let's say, about how many cubic yards? About how many cubic yards? About how many cubic yard? About how many cubic yards of dirt will it take to fill? Will it take to fill the area? The area after the swamp is drained. After the swamp is drained. Okay, so this is kind of common problems. These are what we call engineering problems. So what we can do is we can so you're gonna decide, like, how many measurements you need. So let's assume that you're gonna go about every 20 feet. You decide, depending on the technology and the manpower you have, how many you need. So you also need to make certain approximations here. So what we can do is we can probably ignore that part. So you can start with this is the y naught value. So let's say this is like roughly 13 feet, 13, and then we're gonna go another 20 meters and get another measurement here. So it's gonna be a headache now. Another measurement, so I'm gonna call it y1. So let's call this is 30. You get 30, and then you're gonna go another 20, and I'm gonna call it y2. Let's say this is 40, and then you get another measurement, and then I'm gonna call it y3. Let's say this is 54. You get another measurement. So y4. So let's say this is 76. You get another measurement. Y5. So let's say 122, and you get another measurement. Yeah, it's not up to the scale. So let's say this is y6. So this is, let's say, 146, like that, and probably you can ignore that part, so something like that. Okay, so let's say that these are typical values that you get. So now what we're gonna do is so one gap, so I'm gonna call it one such gap is delta x. So this is equally gaps. Okay, 1 to delta x. So let's say this is 20 feet just for this calculation. Now what we can do is so that's the 13 here you start with, and this is 146, the ending one, and then you're gonna ignore that small part. Okay, so yeah, so like that. So what you do, you're gonna just measure those length, and those you can consider as the y values. Okay, so start with y naught, and then with y to the 6. So what we're gonna do is we're gonna plug in them. So the Simpson answer, so Simpson value, which is equal to delta x over 3, and then we're gonna go with y naught, and then 4 y1, and then 2 y2, and then 4 y3, and then 2 y4, and then 4 y5, and then 6, and then the last one is y6. Okay, so now let's plug in here. So you're gonna get, this is 20 over 3. 20 you decide how many gaps you want to make. So so we're gonna measure at equal distance. So these are all 20. So you're gonna measure by each 20, like that. Okay, so so let's plug in. So you're gonna get 13, and then you're gonna get 4 times 30, and then 2 times 40, and then 4 times 54, and then 2 times 76, and then 4 times 122, and then 146. Okay, so you're gonna do this calculation, and then you can see that you're gonna get 8100. So now we need to know how many cubic yards. So the volume is simply area times the height, area times height. So it is, area is 8100 times height is 5, so you're gonna get 4500 cubic feet, and then you're gonna convert into yards. So if you convert into yards, you're gonna get 1500 cubic yard, 1500 cubic yard, because 1 yard is 3, so you're gonna divide by 27, so you're gonna get this many cubic yards in the lake. Okay, this is a rough value, but this is like really good value, because the Simpson rule is much accurate. So just so this is gonna be like kind of good approximation, and then you can use this for engineering purposes. Okay, so this is the end of the numerical integration and its applications. Thank you.